because the speaker who was scheduled cancelled. So it is a usual convention that in that case, the seminar in charge steps in. Usually we try not to cancel a scheduled seminar. So conventionally, then the seminar in charge gives it. So I'm happy he's doing that. Thank you.
Thank you. Thanks for the introduction. It's a great pleasure to present a joint work with Krishnan Rajkumar. So it's called Telescoping Continued Fractions for the Error Term in Stirling's Formula. And so there are various things here. Stirling's formula, error term, then telescoping continued fractions. And this work is almost over. This work has been almost over for more than a year now. So it's work in progress. So that is why we are not live. We are not showing it live, but it will be recorded, because we hope, if we give up, then we will probably ask somebody to help. So anyway, Stirling formula is about n factorial, and there are a lot of objects where n factorial counts. So on the left, there is this long list of 24 items. They are permutations of 1, 2, 3, 4. So in order, you change the order and you get permutations, and permutations of on n letters are counted by n factorial. So that's pretty, that's where it comes. This list is the list of, 3 subsets of a 5 set. So 5 set. And this is the number of ways of choosing 3 objects from 5 objects. And, in general, n choose k also involves factorials. And there is a third object over here. This is the number of paths. This is called Catalan numbers. So you make paths from 0, 0 to nn, and you can go up north steps or east steps, and you can't cross the diagonal. And then this number is counted by this binomial quotient. It's called the Catalan. So this also shows up. So these are just 3 examples. They come up all over the place. And n factorial is n into n minus 1 factorial. So, and 0 factorial is 1. So it's defined like this recursively, and it gets big very fast. So this is a list of n factorial. So this is 25 factorial. So it's quite huge. Difficult to figure out how big these numbers are just by writing them down. So I've taken the log, and the log also is growing pretty fast. So this is again 25. So log of 25 factorial. But anyway, taking logs is a good idea. And if you take the log, so if you take the log of n factorial, you will get something like this. You get log 1 plus log 2 plus so on with log n. So when you look at something like this, you can think of an integral. And what we will do is we will give you an approach given by Robbins to calculate to come up with the Stirling's formula. So just at the outset, what is Stirling's formula? Stirling's formula is some kind of a asymptotic result, some kind of approximation. And this is y equal to log x. And what he does is he just breaks it into various. So he's really looking at Sn, which is this sum of log p plus 1, p going from 1 to n minus 1. And this point is p, and this is p plus 1. And he's trying to estimate, there's something over here. It's a what Robbins does is so let me expand this chart. So this looks like this. So this is bigger. So let's say this is right. And so this point, this height is log p plus 1. This height, and so this distance is log p plus 1 minus log p. So what he does is he says that let's break it up into 3 parts. So he takes the whole rectangle, the area of the entire rectangle, which is log of p plus 1. And that he estimates by means of 3 items. One is he takes the area under the curve. So he takes the area under the curve. So I'll just write down 3 items: AP plus BP minus epsilon P. So AP is the area under the, so this AP is the area under the whole curve. So it's the integral 1 to p plus 1 of log x dx. BP is this little triangle here, right here. So BP is this triangle. And this is half into base into altitude. So this distance, half of log p plus 1 minus log p. And this epsilon p is this what he calls a sliver, little bit of a sliver. So then he subtracts epsilon p because this triangle contains this curve. Okay, so again, I'm writing it over here. So AP is this integral, BP is fine. To calculate the sliver, I'll just make the picture again. So this time he takes the area under the curve. So this is what we want. This is EP, long P. So he takes the integral again, the entire thing. He subtracts this part. So this is P and this is P plus 1. So he subtracts this. This is log P. And then the area of this triangle, he also subtracts. So minus half of, and again, this height is log P plus 1. This height is log P. So this is what he did. And if you simplify, this is what he did. Okay, so he's got an expression for all these things, and then he sums them up. So when he sums them up, the integrals all sum up. This part telescopes, and you get this, and then you get a minus the sum of the EPs. And you can take the, do integration by parts, and you get this expression. Okay, so he's got up till here, and then there is this EP, which is these little slivers which he's added up. And these he writes as a sum. The sum is going from 1 to n minus 1. So he's writing the sum up to infinity minus this thing. So then he shows that this converges. So he shows this sum converges. And therefore it's some constant b. And then this chap, he leaves it as it is. This sum, and he calls it Rn. So this sum he calls Rn right here. So ultimately you get, include the 1 with the b, you get n plus half log n here minus n plus some constant, and then you take the exponential, so you get this form. Okay, so there is some. So this Rn is the is what we call the error term. The Rn is the error term. This is what we are after. So Rn is the error term. So I should mention that this C is not so easy either. So C happens to be, you can prove it is equal to square root of 2 pi. I won't prove it. It's not so easy. And this is actually what Stirling did. So Stirling actually found this. So he had some estimate, and he did, in the course of his work on interpolation, he did something to figure out what should half factorial be. So he was working in something what we call the gamma function. And then De Moivre proved it. So, the moral of the story is that, it's known as Stirling's formula. So discovery is possibly more important here. Anyway, so I'm not going to show you how to get Stirling. So what De Moivre used was, he used Wallace's product. And you can use the probability integral or the gamma function or the probability integral to get this. There's n number of ways of finding this guy. They're pretty standard. This is what we are after. Okay, so what happened, what Robbins showed that Rn is between 1 over 12n and bigger than 1 over 12n plus 1. And even before that, Cesaro in 1922 had this lower bound for Rn, and many people have looked at lower bound. For some reason, they haven't looked at upper bound, but they've looked at a lot of lower bounds. So Maria is one person who goes like this. And so there are more recent ones too. So what we were attracted by were two things. One is that Maria's lower bound looks like a continued fraction. So this looks like a continued fraction, and these also, of course, they're continued fractions. This is also continued fraction, but they didn't write it like this. Maria wrote it like this. And the second thing is that we note that Robbins used telescoping of series to prove his bounds. And so that is where we got the idea to, let's see, can we combine these two items? So both of us are interested in telescoping. I mean, everybody is interested in telescoping. They think it's the trivialist thing in the world. And both of us were very interested in continued fractions. So we decided, let's see if we can do something there. Okay, so our idea, first of all, what is Robbins' idea? Robbins' idea is that he takes EP and he telescopes it. He finds an upper bound. So he writes it like this. It's some upper bound P minus upper bound P plus 1. And some lower bound P minus lower bound P plus 1. And then by telescoping, so from here to here, you get telescope. And you get the upper bound, and this was Rn. So he's got the bounds from by telescope. Now what we want to do, so our idea in this paper is to find bounds in this form, but this GM function, which telescopes, is actually a telescope, is a continued fraction. So this notation I'm writing to sort of save space. So a continued fraction looks like something like this. It can go on for a while and go on infinitely, and then we just write it. When we write we write a plus at the bottom, but then this part we move upwards. So it's just to save space. This is it's somewhat irritating. It takes some time to get used to this, but it's much better than Hardy and Wright, who just write a sequence and so on. This at least looks like a continuous fraction. So there's a plus at the bottom. You notice this, and there are dots at the bottom, and they're nice tech macros for all these things. Okay, so again, our approach, now more details. So this guy, this was EP, it's 2p plus 1 and times log p plus 1 over p. And it's actually, it comes from this expression, log 1 plus x, 1 minus x, where x is 1 over 2p plus 1. And what Robbins did was Robbins used a series expansion of this. And this guy right here, it has a continued fraction expansion also, like, which looks very nice. So this was, I mean, we were aware of this. I don't know who it belongs to, but possibly Gauss had used this continued fraction already in his work in quadrature. So this was one of those things which was rediscovered by Ramanujan. So we somehow was, it was in our mind. And if x is p 1 over 2p plus 1, it reduces to this. So you can go from here to here. So this is the continued fraction that you want. And there is a theory of continued fractions. Continued fractions, they satisfy a 3-term recurrence relation. And they are very closely related to orthogonal polynomials. And in fact, this one is related to the simplest of orthogonal polynomials. So these are called Legendre polynomials. And these are the associated Legendre. So in the theory of these orthogonal polynomials, Monu, you have a question?
Sir, my question is that this kind of calculation, how we did that? Like here is one, we have a minus sign in denominator. So how we solve this?
I mean, you can, so yeah, that's a good question. I'll just take a short break from my story and just address this. So what you do in a continued fraction is you chop it off. First chop it off here, then chop it off here, then chop it off here, and so on. And then you get a sequence. And then there's some theory of sequences where they converge, they come close to another function. So that's how one handles that. So minus sign doesn't really, minus or plus doesn't really bother. Okay, so I hope, I mean, that's half of answer. So anyway, so if you do chop them off, then you get what are called convergents, and these convergents, you can tell what they are. They are well-known polynomials called Legendre polynomials, and all continued fractions of a certain type can be written in this form. And these are the numerator polynomials are called associated Legendre. So they also satisfy the same 3-term recurrence relation, some slightly mildly different. So these are well-known objects.
Sorry, Gaurav,
Yes.
I'm just not familiar with this notation, this continued fraction notation. So I think that is the question which she was also asking. What is this notation for the continued fraction which you are using?
So instead of writing 1 plus 1 over 3 minus 2 plus 1, something like that,
yeah,
I just put it in the denominator. So this 2 I bring upstairs. That's all. So if there is
that's okay.
That's all. So I mean, we are trying to just flatten it up. That's all.
Right. I think that was what was
Okay. All right. Okay. Thanks. Yeah. So coming back to it, our goal is to figure out this chap, and we see that it is there is some continued fraction associated with this. And so what we do is we want to play around and try to see how can we get a continued fraction. And these objects are well known, so they can be computed. So here's our approach. This is the chap who we isolate now. This is, you chop off this continued fraction, and whatever continued fraction is there, you multiply it by x and subtract 1, and that's an object. And we show that this guy is an increasing sequence of approximations to EP. So this is easy. It follows easily from the continued fraction theory. I mean, everything is minus, so it becomes an increasing set. So this is easy to do. And then we solve a series of inequalities of this form, and I'll be clearer on what we are doing here. For m even, it will be less than something. For m odd, it is less than. And each step, m equal to 1, 2, 3, we find this a1, a2. So remember, our target is that we want to get something like this. Minus a guy with p plus 1. So we wanted telescoping, and we just, at each step for m equal to 1, we calculate a1. If we can calculate, then we try m equal to 2 and so on. So let me show you. But before I show you some examples, some facts would happen. So it turns out that when we calculated them, I mean, these things can be calculated on the computer. Turns out both sides are functions of this p times p plus 1. So it simplifies matters a little bit. So we call this new variable z. So it's easy to show the left-hand side is easy. The left-hand side is easy to show it's a function of this because pk star is an odd function, pk is an odd function, and when you divide it, it becomes an even function. It's an even rational function, and you can tell the degree of this guy. Pk is k, pk star is k minus 1. So when you multiply by this, its degree also adds up. And so it's a function of x square, and if you replace x by 2p plus 1, then you get 4 times z plus 1. Right hand side is much more complicated, so I won't get into that. So, but the point is that you can write it like this. Okay, so now I use some notation before. So this guy x pk star x. I just told you this is this can be written in terms of z. So I just call whatever I get, I just call it fk of z. And let's start with k equal to 2 and m equal to 1. So f2 star over f2 turns out to be 1 over 12 z minus 1. And this is, I'm taking a1 over p minus a1 over p plus 1. And when I simplify, I get it in terms of p plus 1, which is z. So remember, z is p times p plus 1. So I get this, and then if I cross multiply, I get this inequality. I'm trying to solve this inequality, and it turns out that, yeah, a equal to 1 over 12 works. So the leading term, if I get rid of that, put a1 equal to 1 by 12, this becomes 0. The rest remains negative. So so this is wonderful. I get one item. So I've already shown f2z is less than 1 by 12. So remember, there was a 1 by 12 in Robbins story. So this 1 by 12 is the same guy. So this was encouraging. So we took another one. So now we take keep so keep a1 equal to 1 by 12. Go to G2 and try to find if this kind of inequality works. So this is G2p with a2 minus this, and you simplify, you get something like this. So again, cross multiply. So this f2 star and f2 stay the same. You cross multiply, you get this. So again, now 3a2, if I put 3a2 equal to 1 by 6 or a2 equal to 1 by 18, then it works. So this side is positive, and this guy is 0. So again, I can find an a2 so that we get this inequality, some inequality like this. So already I get e2 to be bigger than this chap. This guy minus this guy, and then if I sum over p going from 2 to whatever, n going to, so this is en. So if I keep going, I mean, if I take the sum, I get this. So this is nice. Already it beats Robbins. For n equal to n bigger than 3, it beats Cesaro. And for n equal bigger than 4, it beats Maria. So already we are, all the 3 guys I listed, we are beating them with k equal to 2, m equal to 2, with just this inequality, and we got an inequality. There are more guys, so let's do k equal to 3. So here I'm using this notation. I mean, this paper is a nightmare of notation. This is basically what we get by clearing. So let me, there's one thing I forgot to mention. See, this guy, if we get a if we get a over here, if we get a, so this is if we get a lower bound, if we get a lower bound for pk, right? So pk 2p plus 1 is bigger than something, right? Something, and it's also less than ep because it's increasing. So if we get a lower bound, we get a lower bound for ep2. So in this case, there is no issue, but here upper bound we don't know yet. So upper bound we don't. So if we get an upper bound for pk, it's possible that ep is a little bigger than this guy. So for that we need more information, but lower bounds we are. That is why in this case I already get a value lower bound for Rn, and I'm beating Cesaro and same thing here. So I use delta 1 km, where we, whatever we get on the left hand side by clearing denominators and bringing it to the left hand side. And I calculated, again, I get A1 equal to 1 by 12, and the sign of the remaining terms is fine. So here it's 5 minus 60 A1. So if I put A1 equal to 5 by 60, I get 0, and that's 1 by 12. Similarly, here I get 1 over 30, this time a little different from 1 over 18. Here I get again, so again, the thing which we are noticing is that the leading guy. So in this one, we have already, we've taken A1 equal to 1 by 12, and this we take here, then we get A2. Then here we take A1 values and A2 values, and then we get A3 and so on. You can see what's happening, that just the leading guy has to be set to 0 and we get a value. And the rest, magically the sign comes out. Okay. So in this case, we beat another chap called Nanjundiah. His lower bound. So this is a better than this guy's lower bound. And the best so far which we could find was in 2008 by a person called Popov. He said this, and for that we need to go to k equal to 5 and m equal to 4. So we get this lower bound, and this beats Popov. So far so good. We have what we wanted to do, we have more or less done. In the sense that we wanted to beat Maria first, then we learned that there are more people, then we beat all of them. So then we created a lot of values. So I mean, it's easy to program this. We just programmed it, got a lot of values of A1, A2, and some things which we need to observe. So if you notice, below the diagonal, things stabilize. So you get bigger and bigger numbers, but they're all positive. Below the diagonal, they seem to stabilize, and we do get alternating signs. So let me put down the observations. So again, delta 1 is the left hand side after clearing denominators. The highest degree terms can be made 0 to obtain An. So you can go systematically, do A1, A2, A3. Always the highest degree term, you make it 0, and then that gets you the Am. Am is always positive. Sign of the rest is alternate. So first you get a lower bound, first you get a upper bound, then a lower bound, upper bound, lower bound as you go across the, and value stabilize below the time. So what does value, this is important. What do these mean? So what this means is that suppose we have found pk to p plus 1 is less than some gm p minus gm p plus 1. Okay, we found this, right? And if the value stabilize, so for k bigger than m plus 1, these values stay the same. So you can take the limit as k goes to infinity, and the value stays the same. And in the limit, you've got EP. So that means that this is an upper bound. So whatever upper bound I have found is an upper bound too. So in particular, suppose the first upper bound we found was the first one was delta k equal to 2 and m equal to 1, and this we found where this was less than 1 over 12. A1. A1 was 1 over 12. So it's 1 over 12 P minus 1 over 12 P plus 1. Right. So this was true for all. If we can prove that the sign is correct, it should be less than, then it already proves the first guy. So it proves with P equal to 1, some Rn equal to 1 over 12. So this was what this is what Robbins proved as the upper bound. Okay, so just to summarize, we started this story and we got so EP. We have a sequence PK 2P plus 1 which goes to EP, and we have some kind of way of estimating this guy and this algorithm. So we write down that word. So okay, so this has been proved. There's some notation here. So we have this Fk star over Fk, and we want to less than or bigger than. We had some GM. So we called it DM NM plus over DM plus. So this plus was with P going to P plus 1. So just to simplify the notation, this is what it is. So this was delta 1 K, and we need these associated polynomials, delta 2, delta 3, and then we can prove that if dk is the degree of the polynomial Fk, this guy, and suppose the degree of Fk star is dk minus 1, then we can find A1, A2, Am, which make the degree in Z of these polynomials equal to dk minus 1, dk, and this basically proves that we can get a degree unique guy for degree this. So that it shows that we can find an A1. It doesn't tell us. It tells you can find a sequence A1, A2, A3, but it doesn't tell you the other properties. So at least we know that number 1. This proves number 1. Okay, so we can obtain AM, and then I wanted to just give you an indication of the proof. So to prove it, we use the following recurrences. So we write down delta 1 in terms of delta 2, delta 3, all those associated formulas, and then by some kind of a massive induction on all of them, it seems to work. Because writing this down was not so easy, but once we got it, then the induction is. So using some kind of inductive argument using these recurrences. And what is nice about this set of recurrences is that this helps us program it. So these help us program delta 1s. In terms of, so you can keep AIs alive in terms of Fk star Fk. So sort of like a, this could be like a basis for the calculation, but the program, the this set of recurrences help us program and get the values very fast on the computer so that we can do our. Okay, so what we have proved so far, I mentioned that this is almost done for nearly more than a year. So what is almost done? So this is done. This we have proved. This we have proved, and this we have used another continued fraction. So this paper is a meditation on continued fractions, like you've never seen before. One after the other, we use one continued fraction after the other, and this is still pending. So m equal to 1, we are done. So that means that in particular Robbins upper bound we have got. But m bigger than 1, we are still figuring out how to do it. But we haven't given up yet. So the deal was that at some point, if we give up, then we will ask our friends to help us. And there are friends, who are much bigger experts in continued fractions as well as this. So, but so far we have a great hesitancy to give up. And this has come very close. So it seems like, okay. In any case, even lower bounds, I think, should be publishable because Popov got them till recently. So anyway, so some remarks. This is the numbers that we get, and it turns out that the first few terms match a continued fraction that appears in Jones and Thorne. So Jones and Thorne has this really fat encyclopedic book on continued fractions. And what they did was they expanded the asymptotic series for Rn, which is well known, uses usual stuff. And then there's a way to expand the series into a continued fraction. But they don't do anything with it. It's not clear whether it, we can't figure out whether it converges, it diverges, there is no closed form. So some of the things are there, but we can't prove that we get the same. So, so this is rather strange that by this weird mechanism, we get some numbers, and those numbers happen to be the same. We can't prove that it's the same. In fact, we don't want to prove it's the same, but somebody is going to ask, is it the same or not? And in fact, we can't even prove right now whether our continued fraction converges. So maybe it does. So we haven't proved it yet. But it's not, I would say we want to prove it, but it's not really necessary for the thing. We can leave that also. And the question is that so you have an asymptotic series, which means that as n goes to infinity, it should be equal. And you have a continued fraction. Is it the same? I mean, is it actually an exact formula, that continued fraction? So it gives you lower and upper bounds. If that is the case, then it is something more than an asymptotic. So we haven't really wrapped our head around this. That what does it mean? That if it does indeed become the same, then what does it mean? I mean, okay, is it like a good result or a bad result? We can't tell right now. Okay, I want to also show you a Ramanujan story. I'm going really fast. So if anybody has any questions right now, this is a good time to ask.
Fascinating.
Yeah.
Just a general question. Can we say something about like power series and continued fraction together?
What do you mean?
If given a power series, can be presented in a continued fraction.
Yeah. So any power series,
fraction, power series.
any power series, there is a standard algorithm which you can try to write it like a continued fraction, and it's very easy. I have a paper on that, on how to, it's called How to Prove Ramanujan's Continued Fractions. And basically continued fractions, they appear as Euclid's, for numbers, they appear from Euclid's division lemma. So suppose you are doing, say, 13 divided by 7. So this is 1 plus how much, 6/7, right? I don't know if 7 is a good idea. I think 8 is a better idea. So then you can write it as 8/5. So this is 1 plus 1/1 plus 3/5, and you can keep going on. Okay. So this is Euclid's division lemma, right? You divide it and you take the largest number and so on. I mean, why I was choosing these were Fibonacci numbers. So you can do a similar job. So Euler showed a approach to use a similar job to divide power series. So you can, in particular, you can divide 1 by a power series and you get a lot of standard. So yeah, I mean, it's an easy trick. I can show you at some point. Okay, I hope that answers your question. Sure.
Yes, Professor. Thank you so much.
All right. So to summarize, so far we've got an algorithm. We've proved that it more or less works, except for one item. And if its values stabilize over the diagonal, this proves that we get upper and lower bounds too, if all this happens. And in any case, for any specific value for lower bounds, we can calculate it and do better than anybody else. So lower bound problem is solved. Now, what I want to show you is a Ramanujan story, and I'll leave it on the screen and you read it. So this is a story by Mahalanobis. Can you see my entire screen?
Yes.
Yeah, I'm trying to figure out from the expression, have you read it or not?
Yes.
Okay, Monu, did you finish? So this is really so I mean, one can imagine the scene that Ramanujan is cooking somewhere, and then Malavanis comes, and then he keeps cooking, and then he asks him a puzzle, and then he says, "Here's a continued fraction for the answer," and it gives a answer which is not just one answer but a string of answers. So he solved a series of problems. It's a very famous story, uh, and all he said was, so this is very interesting. In the end, he says, immediately I heard the problem. It was clear that the solution was obviously a continued fraction. And I then thought, which continued fraction? And the answer came to my mind. It was just as simple as this. So this is one of the brilliant Ramanujan stories, one of my favorites. And so what is our goal? Our goal is to say, this is the problem set by Stirling in 1730. Let n factorial be square root 2 pi n raised per n plus 1 by 2 e raised per minus n e raised per rn. What is rn? And then we say, we asked ourselves, the answer is a continued fraction. So which continued fraction? So we gave an algorithm for which continued fraction. So you can take down the solution. It's 1 by 12n plus 1 by 30n and so on. Okay, thank you very much. That's my talk. Yeah. Any questions? Any comments or questions? So my collaborator Krishnan is also here.
This Legendre polynomials enter at some point of time. Is there some reason why they enter?
Oh, that log 1 plus x over 1 minus
Yeah,
x.
that's okay. That's all. Is it?
That when you write it in continued fractions, then that gives you the. Okay. So any further